In these slides, we'll talk about the three types of Fourier transform for discrete time. There are the DTFS, the discrete time Fourier series, discrete time Fourier transform, and the last one is the DFT. Also known as FFT, the fast Fourier transform. These are synonymous. FFT is the fast version of the DFT. We will have some interpretation again and examine the synthesis equation and some examples. Right, why are there three types of Fourier transform for discrete time? It is dependent on whether the signal is periodic or aperiodic. Let's see this example. Xn is periodic. It will repeat every 5 samples. Here, we only have x0 and x1 is 1, same as above, but outside this interval is all 0. So this is an aperiodic signal. So we have a periodic signal and we have an aperiodic signal. Now, in periodic signal, we would apply the DTFS typically. This is the analysis equation. The analysis equation means that we take the input as xn and we produce the frequency representation. The typical symbol of the frequency representation is Ck, and now you remember that here the k index is the k number from 0 to n minus 1 representing the frequencies. So this is the equation for analysis. Now if we have Ck, the frequency representation, we can get back Xn. So here is a synthesis equation. The synthesis equation means you take the Ck's that you produce and you can reconstruct back to get Xn. We only normally just reconstruct n equals to 0 to n minus 1. And you of course can reconstruct n to 2n minus 1, 3n to 3n minus 1. It doesn't matter because it's periodic. But for periodic signal, we typically reconstruct the first period. Now, so this is for the periodic signal. So the genius of Fourier basically say that given any xn that is periodic with n samples, we only need to use k equals to 0 to n minus 1. We only need to use n frequencies of complex exponential to reconstruct it. So that's the genius of Fourier. See? Fourier says to reconstruct xn, just find the correct coefficients weighting. Ck's are complex numbers. You will generate magnitude and phase, multiply by the complex exponential or all this k frequency from k equals to 0 to n minus 1. That's it. So that's the genius of the Fourier transform for periodic signal. You don't care about any other frequencies. You only care about this frequency at 2 pi divided by n times k. Okay? Now, in most books, we will stop here and we say that if this is a periodic signal, we use the DTFS. But actually, you can use the discrete time Fourier transform. What is discrete time Fourier transform? Well, it's actually the bottom line here. The Fourier transform is nothing but it's a Fourier transform of a periodic signal. But it can also be applied for periodic signal. The key idea is this. The coefficients of x omega becomes continuous. However, because xn is periodic, only frequencies at these intervals are of interest. So in the discrete time Fourier transform of periodic signal, we should actually calculate Ck first and take the Ck value and put deltas at these frequencies multiplied by 2 pi. Okay, that's the idea. And in the synthesis equation means that if we have x of omega, how do we construct back xn? This is the equation. Alright, so this is the two equations that you can use for Fourier transform of periodic discrete time signal. Now, what happens when the signal is aperiodic? I'll give you two examples of aperiodic signal. One is finite sample, means I have one here, followed by all the rest zero. The other one is an infinite samples. For example, half to the power of n un. It's a causal signal, and it doesn't go to zero. It will go to infinity. Now, in these two cases, they are both aperiodic. In aperiodic cases, we have this equation to find the analysis equation. How to calculate x of omega. What is omega again? Remember, in the magnitude and the phase figure, omega can be calculated from 0 to 2 pi. That's the key idea. Or if you want to, it's minus pi to pi. But typically we calculate from 0 to 2 pi, and we wrap this guy around to here later on. So what do we do? How do we calculate DTFT of an aperiodic signal? The equation is this. You take xn, and for the values, for all its value, n equals to negative infinity to infinity, xn must be multiplied by e minus j omega n. And this omega is this omega. So basically, if you're writing a soft program to solve this, you substitute omega at this interval at every point from 0 to 2 pi, and you compute this sum. And therefore, it's obvious now that you can only compute this sum when x of n has, finite non-zeros. Here is 2 of them. The rest are 0. So we don't care. This equation reduced to sum of n equals to 0 and n equals to 1, because at these 2 points. The rest are 0. So it's very, very easy to find the DTFT when the samples are of finite support. That means only a finite number of them are non-zero. Here you're almost finished, right? You think I have here there is 0, that's okay, but from 0 to infinity is non-zero value. Okay, so you can't simply by brute force write a program to do this. We'll find other analytical way to solve this. And in our class, we are only able to solve for the geometric series or certain kind of sequences that will converge down to 0, and this series exists. Okay, so that's the idea. Maybe one point to note is that you will often ask whether this Fourier transform exists, and the condition for existence is that as long as we can sum this sequence absolutely, that means all the values are absolute first and we sum, and it's less than infinity, then x of omega exists. Right, once you have x of omega, which is the magnitude and the phase spectrum of xn, then we can reconstruct xn by this equation here. So the synthesis equation is the same. The analysis equation is slightly different. The analysis equation is this equation here, but when it's periodic, it's this equation here. Right, then you'll be wondering, hey, this guy, you keep on summing, it will go to infinity. So this is a sufficient condition, but not the only condition. Okay, so we will not go into these details, but please remember this. Alright, finally, we have an aperiodic sequence. So it's all these dash values here and the dash value outside. But let's say we are only asked to analyze n samples. For this example, 5 of them, only 5 samples at n equals to 0, 1, 2, 3, 4. And in fact, it looks like the guy above. But outside these 5 samples, it doesn't look like anything above. Now, so what? Well, the DFT equation, discrete Fourier transform equation, if you compare these two, if you compare the DTFS equation, which is summing n equals to 0 to n minus 1, this expression here, versus this expression here, they are identical. So the DFT and the DTFS are the same here, except the DTFS will scale by 1 over n, while the DFT doesn't. Well, then you will say, isn't DFT, just a scaled version of DTFS? And you'll be right. So in fact, DFT, examining this guy, 5 samples, is almost treating like the same 5 samples that is repeating. But we already see that it is not the same. So DFT is actually a DTFS in disguise, and this analysis equation and the synthesis equation is only valid, or I should say, the synthesis equation, when we reconstruct from the DFT, this is only valid for this range. And outside this range, which is here and here, these two range, outside these 5 samples, they are not valid. This is unlike the DTFS synthesis equation. When we reconstruct, yeah, we can reconstruct at different cycles as well for the n that is outside the first fundamental period. Okay, so this is the 6 equations of the Fourier transform of discrete time. You must memorize this, and you can use the different analysis equation for different types of signal. I have drawn a mind map for you. So this mind map, let's trace it together. X of t, which is the continuous time signal, is sampled. It becomes x of n. Now, if x of n, if this is periodic, it goes down here. You use ck for the analysis. You will find the magnitude and the phase spectrum from ck. If you want to, if it is aperiodic, then you would use this equation over here. You use this equation if it is aperiodic, and if it is periodic, you'll use this equation over here for DTFT. So trace the arrows and see how do we go from one position to the other. And you realize that if you are an engineer, you are doing this every time. You're taking a sequence of numbers and you're performing DFT or FFT on it. So this is the equation for the DFT. And in fact, this is what you will do in the lab. I give you a sequence, you perform DFT. And if you want to find DTFS, you follow this arrow down. Okay? And if you want to do inverse DFT, you follow this arrow up. So this is the two things that MATLAB will give you. DFT, inverse DFT. We call it FFT and IFFT, the fast version of DFT and IDFT. The rest, actually, MATLAB couldn't help you to solve. Okay? So please get these arrows and as well as the direction of how we can go from one representation to the other. Thank you.